You tell me. Okay. All right. So now that we have a free energy that is polarization and temperature dependent, actually this is a very powerful thing because, well, with one addition, by the way. Now let's make for the first time a precision that applies only to ferroelectrics. If this is an electric polarization or an electric dipole per unit volume, we know that dipoles couple to electric fields by simply the dot product of the dipole times the electric field, right? A polarization couples to an electric, therefore the energy of a dipole in an electric field is something like this. Okay? This means, by the way, that the dipole will align to follow the electric field, because when they are parallel, the energy goes down. Okay, when we have polarization, it's essentially the same. We divide by the volume, and this transforms into P minus E. Okay, and something I haven't emphasized, but I have to say now, is that this energy will typically be an energy density, a free energy density. So this quantity will typically have, in most treatments that you are going to find out there, units of energy per unit volume. Okay? And this thing here also has units of energy per unit volume. So actually, if we want to expand this energy a little bit and make it depend on two externally controllable quantities, let's say the temperature and the electric field, we would write it like this. Okay, and this is a very, very important expression. It's for a very simple system, so the polarization is only a scalar. So we are talking about a uniaxial polarization. Let's say this would correspond to what would be a uniaxial ferroelectric. The mathematical form is the simplest possible, so only two parameters. Only one of the parameters is temperature dependent. The temperature dependence is the simplest possible, linear. The other parameter is constant in temperature, etc., etc. But this is quite a beautiful object because it allows us to compute the energy of the system for any temperature, any electric field, and any polarization. And if we can do that, we can immediately track the equilibrium states of the system for any temperature and any electric field by minimizing this free energy. Okay? So let's do that now. To minimize this free energy with respect to the polarization, we have to consider, of course, the first derivative of the polarization. The first derivative with respect to the polarization, which at equilibrium has to be zero. And this means that we have this expression. This expression has to be satisfied. And this really is a very powerful expression. This equation is called equation of state. And it says that all the equilibrium states of the system have to satisfy this. Okay? And in a second, we are going to see the consequences of that, or how many things we can compute with that. With that, we can compute essentially all the properties of this simple system that pertain to its polarization state and how it reacts to an electric field. Now we have, in order to be in equilibrium, when we say equilibrium, we typically mean a stable equilibrium. And so to check if we are in a stable equilibrium, the first derivative is not enough. In principle, we should look at the second derivative, which has a name. We call it kappa. This is the stiffness coefficient, stiffness. Let me write it here. Stiffness coefficient is also the curvature of the energy around the equilibrium point, of course, and is the second derivative of the free energy with respect to the polarization 2 times at equilibrium typically. And this thing has a very simple expression as well. It's alpha prime T minus Tc and this stiffness coefficient has to be 0 for the system to be in a stable equilibrium. So let's make room and draw these things somewhere. Let me remove this one. I'm going to write here the equation of state for our very simple Landau model. And the definition of the second derivative, which we call stiffness. Well, the definition, not the expression. Okay, so let's solve the equation. Now, let's try to solve this equation of state in a simple case when we have no applied electric field. Okay, so from now on, for this video, the electric field is 0. And we have to figure out the solutions for this equation. But then it's quite simple. I can take P as a common factor, and I have essentially P multiplying alpha prime T minus Tc plus beta P squared. This thing is failing me. This has to be 0. So obviously this thing has two solutions. Solution number 1 is P equal to 0. And solution number 2 is the expression in the parentheses is equal to 0. And the expression in the parentheses is 0 if P squared equals minus alpha prime T minus Tc over beta. Sounds good, right? Now I have two solutions. So I have two equilibrium points, well, three equilibrium points. One is P equal to 0, and here I have two different equilibrium points. But I have to see if these things exist, right? So P equal to 0 always exists. The polarization can be 0 in principle. But here I have a square. So actually the polarization, this solution exists only if what I have here on the right-hand side is positive. So this thing has to be positive, right? And since we have hypothesized that alpha prima and beta, they are positive constants, this will be positive only if T minus Tc is negative. Therefore, this is true only for T smaller than Tc. So this solution, we have to worry about it only for below Tc. Above Tc, these solutions don't exist. And the second thing that we have to check is whether these solutions are minima of the energy. So we have to evaluate the stiffness coefficient. So for the first one, it's pretty easy. P equal to 0, I plug it there, I get alpha prime T minus Tc. Now the solution is stable if the stiffness is positive. So this guy has to be positive, and this is positive for, this happens, for T bigger than Tc. Again, alpha prime is a positive constant. So we have a very interesting situation already, because for temperatures above the transition point, there is only one possible solution. It's a minimum, that's good, which is the solution with P equal to 0, which we already knew graphically. Now, for temperatures below Tc, this solution is not a minimum, it's a maximum that we already knew as well. And of course, these guys are going to be the two minima that are equivalent, right? We have plus and minus something. But just to make completely sure, we have to check the curvature. So we have to plug this p squared in there. So we have alpha prime t minus tc, and then 3 times beta. P squared is that, so is 3 times beta simplifies with beta, alpha prime t minus tc. So the whole thing goes to minus 2 times alpha prime t minus tc. We are at temperatures below Tc, therefore this parenthesis is negative. Here I have a negative sign, so this thing is positive. So it works. What we already knew from our simple drawings is, let's say, confirmed and corroborated by the trivial mathematics when we look at the first and second derivatives of the free energy. So from this mathematical solution, now we could actually go back and plot, for the positive polarization maybe, a very careful and specific shape of this polarization versus temperature. Above Tc is 0, that's easy, but below Tc, the polarization is the square root of this thing. Okay? So it goes with the square root of the difference in temperatures, and well, it has an interesting feature, which is that the slope here goes to infinity, and we will look at this feature later, but it's going to look at that. It's going to look like something like that. Okay? The only salient feature is the slope at which this thing comes at Tc. All right, so we have figured out our first analytical expressions that define really everything that the system can do when no field is applied. And then, of course, these polarizations are spontaneous polarizations because we haven't had to apply any electric field to generate them. Okay, we stop again.